Hi. Let's solve some problems. I hope. This is too long for problem A. Okay, this is confusing. So we have some sequence of data. Basically, we have two counters. Both of them should start with zeros, and we know that if the second counter increased, then the first counter increased at the same time. This paragraph is hard to comprehend, but okay. We have to check if there were these two counters, then we start the process and record the value of counters in some chronological order, and we have to check if it can be the correct sequence. So basically we have to add 0, 0 at the beginning and then check if between two consecutive checks the increase in the second counter is not more than increase on the first counter, and both counters do not decrease. Okay. Sure. Whatever. So we have multitest, and we actually can find the contradiction before reading the whole input, but we have to read the whole input every time because we have multitest and we want to read the test case before proceeding to the next one. So we will maintain check everything online. We won't store the data, but we have to read everything. So we will have the last value of counters, and n times we have to read the new ones. And we have to check some things. They shouldn't decrease, and the second one should increase not more than the first one. Great. This is actually a nice problem. We have n people. Each of them has some initial amount of money. We say that a person is wealthy if he or she has at least x money. We can take some subset of people and take all the money from them and then return the money, but redistribute it equally. So each person will have the average. So yeah, once again, we can take some subset of numbers and change every number in this subset to the average of this subset. We can do this as many times as we want, and we want to maximize the number of wealthy people. Okay, so the main idea is that we can sort all the people and it's actually not easy to prove. So I want to say that we should sort the people by the money they have. And then we should take some suffix of these people, redistribute money among them, and just do nothing else. And we're good. The number of wealthy people we will have is the length of the suffix, and we have to choose the suffix such that it is maximal, but Maximal with properties that the average is at least x. It feels pretty obvious to me, but I'm not sure how to prove that. No, we can try to prove something like this. Let's say that we will maintain all the numbers sorted, and when we do some operation, let's say we choose 3, 6 and 9, and we will change them to their average. We'll do this like continuously. The numbers that are bigger than average we will slowly decrease to the average, and the numbers that are smaller than average we will slowly increase continuously. And like we can see that in their average is 6, so we'll change this to 666. But that's not sorted. We should swap these two numbers, and like we will do this when they became equal. We slowly decreasing 9, and when it will become 8 we will swap them, and then continue slowly decreasing, so the array will become this. So what I want to prove is that the sum on every suffix is not increasing. Every operation cannot increase the sum on some suffix. Well, why is that? Well, that's because basically lower numbers are closer to the beginning of the sequence, and when we do the averaging, the numbers that are closer to the beginning will increase, and the numbers that are closer to the end will decrease. And let's look at some suffix. If the numbers are if no numbers on the suffix is increasing, then obviously the sum cannot increase. But if some numbers on the suffix are increasing, I want to say that the total decrease is actually bigger, because like there is some divider such that to the left of this divider numbers will increase, and to the right they will decrease. The total sum stays the same. So if on our suffix some numbers are increasing, then all the numbers that are decreasing also on our suffix, and maybe on the corresponding prefix there are also some numbers that are increasing, but there cannot be numbers that decrease. So the sum on prefix will increase. That means the sum on the suffix will decrease, because the total sum should remain the same. So we have proved then that on each suffix the total sum will slowly decrease. It cannot increase after any operation. And in the end, well, the numbers are sorted, so obviously the numbers that are at least x will be some suffix. The average on the suffix should be at least x, and that means that in the beginning that also should be true. The average on the suffix is at least x, because it could only decrease in the process. So we can, instead of doing our complicated process, which resulted in us taking the suffix, we could just average everything on the suffix and take it. So my initial idea was correct. Not that I doubt it, but it was really hard to prove. So to implement it, we will read the numbers, sort them, and then we want to find the largest suffix with average at least x. To do this, we can well, basically we can subtract x from each number, and then we want to find the largest suffix with non-negative sum, and we can do this greedily, but we don't have to like first subtract x and then find the largest suffix with non-negative sum. We can do this in process. And that's all. So I'm going from right to left, and if the sum is still at least 0, then I'm adding this number to the suffix, otherwise I'm stopping and printing the answer, the length of the suffix. In problem C, we have n monsters staying in the circle. Each of them has some initial health and parameter b. We can pay 1 and decrease the health of a monster by 1, and when the health becomes not more than 0, the monster dies and explodes and deals BI damage to the next monster in the circle. And we want to calculate the minimum sum we have to pay to kill all the monsters. It doesn't make sense to damage some monsters and then switch to the other monsters. Well, basically the amount of damage we have to do is constant. It's just the sum of health of all the monsters, and like the amount of bonus damage which is free for us is also fixed, but some bonus damage can be wasted if the health of monster after the after explosion will go below 0, and we want to want this to happen as as small as possible. So we don't want to decrease health of a monster if we don't want to kill him, basically. On the other hand, we can look at this from the different angle. Let's let's look at some monster and let's look at previous monster. If we kill the previous monster, our monster will incur b I-1 damage. If his health is not more than b I-1, then he will die. But if it is bigger, then he won't die, and we have to incur more damage, and this number of damage we have to do is his initial health minus the amount of damage the explosion of the previous monster does. We will have to do it, so let's do it right now in the beginning. So for all monsters that won't die from explosion of the previous one, let's do the damage. After we have done this, we incurred all the necessary damage, so we didn't spend anything we don't have to, but now every monster will die if the previous one was exploded. So if we will kill any monster, it will explode, then the next one will explode, then the next one will explode, and they all will die. So we will just kill the one with the smallest health, and we are done. Since it is not worth to do the initial necessary damage in the beginning, we can do it in the beginning and then we act optimally. So we have to kill the first monster by hand, and we do this in minimal damage, so our strategy is optimal. This is also a very nice problem. So I will go through all the monsters. The previous one is monster P. I have to be careful with cycling. And if our health is strictly bigger than the damage of explosion of the previous one, we will add the difference to the answer and say that our new amount of health is exactly the damage of explosion. And now just calculate the minimum of all the health and and print the answer. In problem D, we have a complete directed graph on n vertices. So we don't have loops, but for every different u and v, we have directed edges uv and vu. We have to find a cycle that visits every edge exactly once. We will write this cycle as a sequence of vertices. We visit in order, and we want to find the lexigraphically smallest such cycle, and we asked to print some segment of it because the cycle itself has a quadratic length, but n is up to 100,000. When we want to minimize something lexigraphically, the main path to follow is that we want to first minimize the first number, then the second one, then the third one, and so on. So if we have some fixed prefix of answer and we thinking about what to do next, we have to go to such a vertex that like we have this edge, we can end the cycle, and this vertex is minimal possible, the next one. So we want to start from vertex 1. Then we will probably go to 2. Let's try to write something down. So we will start at 1. Then we will go to 2. Then guess we should go to 1. Well, if we can return to 1, that's the best possible option. Then we want to go 2, 3, and so on. Now we can't go to 1, we don't have loops. We cannot go to 2 because we have already used edge 1, 2. We will go to 3, and so on. We will like go 1 from 1 to all the other vertices in increasing order and back. So 1, 2, 1, 3, 1, 4, 1, 5, 1, and so on. Let's say we are working on n equal to 5. So now I want to go to 1, but that's a bad choice because we don't have any edges left to go from 1. But we didn't visit all the edges, so we can't continue. So we have to do something else. And the second best option is go 2. We can't go to 1, we can go to 3. Oh, we can go to 2, we can go to 3. Now, well, we can't go to 1, I already use this edge here. We'll go to 2. Then probably we want to go to 4, then 2, then 5. We could go to 1, but there are some edges that we didn't visit, so and we cannot escape from 1, so we won't do that. We can't go to 2 because we already used this used that edge, so we will go to 3. From 3 we cannot go to 1, we can go to 2, we can go to 3, we'll go to 4, then 3, then 5. We can't go to 2 and 3, we already used that edge. We cannot go to 1 because there are edges 4, 5 and 5, 4 we didn't use. We'll go to 4, then 5, then 1. So the pattern is pretty clear. We will basically we are writing down all the pairs of numbers we can make from numbers from 1 to 5 in lexicographically increasing order: 1 2 1 3 1 4 1 5, then 2 3 2 4 2 5, then 3 4 3 5 4 5, and then 1. And well, it looks like well, basically by how the lexicographical ordering works, we kind of proved by construction that that's what we have to do. The construction that I used can be done for any n, and we cannot do anything better on any step of the algorithm, so the construction will be like this, and we just have to implement this. So we have to find a way to print some segment of these numbers. It's not really hard. We will divide the sequence in the blocks by what is the first number in the pair. There will be n-1 such blocks. For each block we know its length, so we'll basically build the sequence as a sequence of blocks and then print the numbers we have to print. As I already said, the length is quadratic, and n square is 10 to the 10th, which is bigger than int, so L and R should be long. So we have one based indexation here, and I don't like it. So now I want to go from L included in 0 indexation to R not included. So now I will go through blocks. This should be long. This is the index of first value in the block. The length of the block is n minus v times 2 because we have pairs, but I'll use len as like number of pairs. So the length of each block is also O of n, and we have to print some segment of the sequence, so we will have like most blocks in the middle taken fully, and maybe one or two blocks on the ends which are not fully taken. So if I will construct this one or two blocks fully, it won't affect the running time. So I'll just do this. So we have to like the next block will consist of 2 times len numbers. So if we don't need any of them, then we will just keep them, and that's all. Otherwise, we will construct all of them and print the necessary ones. So the next pair will be VU. If like we have to print it, then print V and increase L, increase S in any case, and do the same, but now print U. Oh yeah, we have one in the end, so if we didn't finish, print one. In problem E, we are given a number D, which is very big. we will find its divisors and construct a graph such that the divisors are vertices of this graph. There is an edge between two vertices if well, basically if they differ only in one prime divisor. So if x greater than y and x is y times some prime number. The length of the edge is the number of divisors of x such that they are not divisors of y, where x is larger and y is smaller, which actually says that it's the number of divisors of x minus the number of divisors of y. And also well, okay, doesn't matter. We have to, for given two vertices in this graph, we can find the shortest path between these two vertices, but we have to calculate the number of different shortest paths, and we have to do this not once, but there are many queries of this type. This looks insane, but I guess it shouldn't be very hard. I don't know. Okay, so let's unravel. So first thing that we to use is that each number has the form as a product of prime powers. If we have all these numbers are primes, there is powers and their product. If we have this form, then the number of divisors is product of such brackets. Every bracket is power plus 1, power of this prime. Why is that? Well, because every divisor of x should have form like the same primes, but in smaller or maybe equal powers, but not greater. If the power is greater, then it is not a divisor of x. So when we have two numbers between which we have an edge, so we have y and we have x such that it is y times some prime number, let's say p1. what are the numbers that x have but y don't have? Well, the divisors of x is numbers that has the same primes but in maybe lower powers. If the power of p1 is strictly lower, then it is also a divisor of y. We can see that it has the same form as the divisor of y. So the divisor of x that is not a divisor of y should have p1 in power a1 plus 1. And all other don't matter because we know that it is not a divisor of y. So the weights of this edge is a2 plus 1 times a3 plus 1 k plus 1. So now when we have two vertices between which we want to find the path, well, they have some primes for which they have equal powers. Then they have some primes for which this vertex has greater power. And finally they have some powers, some primes for which this number has greater power. It's not good that I'm using the same letters, but how can we go from this vertex to this vertex? Well, we can either multiply by some prime or divide by some prime, but we cannot go higher than the number we had, but like had in the beginning, number d. But both of these numbers should be divisors, so that shouldn't be a problem. When we multiply or divide by some prime, we either increase or decrease this power. And like the length of the edge will be the product of ai plus 1, like this thing, for all the primes except the one we changed. And basically we want to decrease all these powers and increase all these powers, because these are bigger than we want and this is smaller than we want. We could do something else. We could like change these powers and then go back, but for some reason I don't think that it is useful. We want our path to be shorter. I think that the optimal strategy is in some order decrease the powers here, so that they will be equal to the powers here, and then in some order increase the powers here, so that they will be equal to the powers here. Why first decrease then increase? Well, because the costs are the costs are bigger when we have bigger powers, so we want our powers to stay low. So we want first to decrease, then to increase. Why shouldn't we decrease something and then increase them back? Let's look at this this way. We can also use this number. That's what I wanted to say first, but I didn't think that it is important. Is the number of divisors of x minus number of divisors of y. We can either deduce it from these formulas, like for x it will be a1 plus 2 here and everything else here, then for y it's just this, and we will subtract them, all this will remain the same, and here we will have 1 and get this formula. Or it's actually pretty simple. All the divisors of y are divisors of x, so the number of divisors of x that are not divisors of x of y is just the number of divisors of x minus the number of divisors of y. So if it is true that we have to decrease v, like divide by something, and then increase to get u, let's say that we will go like decreasing, get the lowest point, and then go increase. Then like when we decrease on this part of path, we will always get like the number of divisors of this minus the number of divisors of the next one, then plus the number of divisors of that one minus the number of divisors of next one. So on each segment of our path, the total weight is the number of divisors of the first one minus the number of divisors of the last one. So the length of this path is actually number of divisors of v minus the number of divisors of w plus the same thing as here, but here it's like the number of divisors of last minus the number of divisors of first, because like we're going backwards, we're increasing numbers, so it will be d of u minus d of v. Then it is easy to see that if it was true, then we want this number to be as big as possible, and it is kind of obvious that it is like don't touch these primes. For these primes, like for all primes, take the lowest. Basically, it is GCD of these two. Why shouldn't we do something else? Maybe do some increasing, decreasing, increasing, decreasing. I don't know. Well, it kind of follows from the thing that we want our powers to be as low as possible, and also we don't want to do some unnecessary stuff. I think that we have to somehow prove by induction that for any two vertices the length of shortest path is this number of divisors first one plus number of divisors second one minus 2 times number of divisors of their GCD. The induction will be on the length of this shortest path. It is true for 0 lengths. So if v and u are coinciding, then this is 0. And it is true for our edges, because like v and u different in one prime. The GCD is like, let's say v is greater than u, then w is just u, so this is the number of divisors of v minus the number of divisors of w, which is the number of divisors of u, and this is the length of edge. So let's well, basically look at the smallest counterexample. Let's say that we will take v and u as the smallest the pair with the smallest distance between them that is not that thing. It should be smaller because we can construct a path with this length, and it cannot be just one edge, because for edges it is correct. So there should be some middle point, and for that middle point the formulas are correct. So the shortest path from let's say that have some path to some middle point, and then we go to u. We know that the length of this part is like correctly calculated using this formula, and the length of this part is also correctly calculated using this formula. And we want to show that sum of this length is at least this formula for v and u. So let's say that GCD in this part is the GCD of v and mid is g1, and GCD of mid and u is g2. Then the length of this path is dv plus d mid minus d of g2 times d of g1 plus d of u plus d of mid minus 2 times d of g2, and I want to prove that this is at least d of v plus d of u minus d of w, where 2 times d of w, where w is GCD of v and u. So we can simplify this, raise this, and divide by 2. And after all of this, we want to prove that d of mid plus d of w is at least d of g1 d of g2. Okay, I can prove this. Let's look at some number x. What I want to prove is that the number of times x is the divisor of mid or w is at least as big as the number of times x is a divisor of g1 or g2. Let's suppose x is not a divisor of mid. Then it is also not a divisor of g1 or g2 because g1 and g2 is GCDs of mid and something. So this is at least 0 and this is 0. If x is a divisor of mid, then like the only possible contradiction can be if it is also a divisor of g1 and g2 but not a divisor of w. But since x is a divisor of g1, it is a divisor of v because g1 is GCD of v and mid, and it is a divisor of u because it is a divisor of g2. So x is a divisor of v and u, so it is a divisor of their GCD, which is w. So this inequality is correct, and this inequality is correct, and we have proven our claim. Whew. I also now I have to calculate the number of such minimal paths. Guess I have to prove that there is no other way like other than this type, but I won't do it. I will just state that we have to decrease to w and then increase to u. So we have to calculate the number of decreasing paths from v to w and the number of increasing paths from w to u, and then multiply them. Any decreasing path is okay because like how can we calculate the length of this path is well, it is dv minus dw in any case, in any path, like as long as it is decreasing, we always divide by something. The length will be the same. So we have some divisions, some prime numbers we have to divide by, and we can do it in any order. So we have to multiply by some multinomial coefficient, like the number of paths is the number of ways to arrange the divisions by the prime numbers we have to do. To calculate it, I have to know like in what prime numbers they are different. And to do this, like all these numbers are divisors of initial number d. I will factorize this number, remember all its prime divisors, and for these two numbers I will calculate their representation in this form. I just know that all their prime divisors are prime divisors of d. For each of them I can calculate the power just by like try to divide while it's dividing. It will take logarithmic time because the total sum of these things is logarithm of d, because like if I will change every this prime number to 2, I will not increase the number, and thus I will get 2 to the power of sum of the prime powers of powers. So if this power is greater than logarithm of d, the number will be greater than d, which is not possible. After that, I will calculate the same thing for GCD, which is just taking minimums in every power. Then I have to calculate the multinomial coefficients, which I think I will well, I can calculate factorials and inverse factorials, but I guess I will be okay with just using binomial coefficients. And that's all. Well, that was a long problem. Well, if I would be on the contest, I will just write the solution right away, because like everything looks obvious, but to prove it actually is not that easy. So let's calculate binomial coefficients using the Pascal triangle. Now let's find all the primes that divides d. I don't have to remember what in what powers they divide d. I just want to know the primes themselves. I will find powers for x and y. So now I want to calculate multinomial coefficients. The power for GCD is minimum, and I don't know why I'm calculating two answers, and I'm only changing them by multiplying by something, and the answer is their product. So I could just calculate one answer. So how does that work? Well, multinomial coefficient is stuff like that, but we can also write it as a product of binomial coefficients, something like that. So it is well, basically I will multiply and divide by factorials of all the prefix sums, and then regroup the formula. So I will get something like so this is binomial coefficients that I'm multiplying here, and you can see that this is just one, and like this and this are equal. I'm multiplying by this and then dividing by this, and this are equal. This and like the next one are equal, and they will all cancel out, and what will remain is this and all the factorials, all the individual factorials, and this one, which is not important, and we will get this. And it's not working. Interesting. problem F, there is a function that given an array calculates an array of its prefix maximums. We store the value in the result if it is strictly bigger than all the previous values. So if we have this array, we will store the first element, we will store the first element, then we will skip the next two because they are smaller, then we will record 7, then we will skip the next 4 because they are smaller or equal to the previous 7, and then we store 8. We have an array, and we also have the prices that we have to pay to remove the is element of this array, and we want in the end to get like we can remove some elements, we will pay some prices, and we want to get the array such that when we apply this function we will get the array B which is given for us, and we cannot change it. Okay, for sure I don't have time left to solve both of the remaining problems, so I'll try to solve this one in time. Okay, so the main idea is that we will use dp. Let's copy something. So we have our initial array, and there is an array we want to get as result. Like we first delete something, then apply the function. So each of these numbers we should leave in the array. Not all of them, but for each of these numbers there should be a place where which is not deleted, and after the application of the function which erase everything except for the maximums, it should also remain. So for example, it could be these places. Our dp will be from the place in initial array, and we'll say that we will not delete this number, and it will correspond to the same number in the array we want to get. And we have done everything correctly on this suffix. So we have erased something such that like starting from this number, we are assuming that nothing bad will happen in prefix, so we won't get anything greater or equal than this number, and we will find all the previous numbers we want. Starting from this place, everything will be fine. We'll record this number and then record everything we want on the suffix. And like this dp will be to minimum cost. How to calculate it? We'll calculate the dp going backwards from the on the array we want to get. Like basically, suppose we calculated the dp values for all the occurrences of 10 in our array. Now we want to calculate the dp on the all occurrences of 7. How to calculate the dp value for given occurrence of 7? This one or this one or this one? Well, we have to choose what will be the occurrence of 10. We want to be in the ending array. We will take dp value from this, and then like for example for this 7, on the segment up to this 10, there are some numbers. The numbers that are strictly greater than 7 we have to erase, otherwise this won't be the array we will get. And all other numbers we can erase or we can leave them, it doesn't matter. Well, obviously we want to erase only those that have negative cost. So for each occurrence of this 7, we want to try all the occurrences of 10 on the right, then calculate the sum on this segment of the costs and do a transition. We have some obvious problems. The first problem is that we have to somehow calculate the sum to do this, we will maintain the sums in some data structure. For example, Fenwick tree will maintain costs for each number. Since we are going in the backwards order of numbers, they will decrease, and like some numbers for tens were not. We didn't have to erase them, so the costs were just minimum of 0 and their cost. And for 7, this number will be we'll have to erase it, and the cost is just the cost. So the solution to this is that in the same time when we are calculating our GPU going backwards through this array, we'll do some kind of scan line on the all numbers, and when we have to like turn the number on, if it becomes greater than the current number we are working on, we will change its cost in the Fenwick tree. So we can take the sum here in logarithm time. The second problem is that there can be many tens, and if there are many sevens and many tens, our solution will have quadratic time. Like we want to work in time linear on the sum of number of sevens and tens. If we'll do that, the total complexity will be linear, well, multiplied by logarithm of Fenwick tree. So we'll do again like 2 pointers on the positions of sevens and tens, going from right to left. Like for basically when we have like suppose there are some more tens here, if we pass some tens, what we want to know is like what is the minimal cost of doing everything right like up to this place. So we could either like use this, for example 10, and already fix this segment. We know that we are working on sevens, so we know what is the cost to fix this segment. Or we could use this 10. So we're going from right to left, maintaining what is the minimal cost of doing everything right up to the leftmost 10 we got. When we are passing 10, we will use the best on the current suffix and add the cost on the new segment, or we can just use the new 10, and when we are passing the 7, we'll use the calculate minimum value, add the value on the segment to this leftmost 10, and calculate the GPU value. So the total complexity is n log n. I have 10 minutes, which is not enough at all, but let's try, why not? the contest has ended. That's unfortunate. Well, it should work. Thanks for watching.